We can show that in general, small perturbations from a circular orbit will create a new elliptical orbit. On the original circular orbit, we can write the body's position and velocity vectors as, where we're using the same setup as we did for the Euler-Hill equations. We have our rotating Hill frame, where the coordinate origin O is a point on the circular orbit, ER is the orbital radius direction, E theta is orthogonal to that in the plane of the orbit, which means that it is the velocity direction of the orbital velocity for the circular orbit for all time, and EZ completes the triad and is in the direction of the angular momentum of the orbit. So the position of a point on this circular orbit is always given by the radius of this orbit, which we've previously called R1 in the ER hat direction, and the velocity of the orbit is always in the E hat theta direction and has a magnitude of the circular orbit velocity, which we've previously derived as being the square root of the gravitational parameter of the central body divided by the orbital radius. We will now consider a small perturbation to the magnitudes of these two vectors of the form. So we are modifying the initial orbital radius by quantity delta r and the initial circular orbit velocity by quantity of delta v. At this point, it is useful to introduce a new parameter, the flight path angle, which is defined as the angle between the local horizontal and the velocity vector. And this definition allows us to write the magnitude of the orbital angular momentum, magnitude of r cross v, as rv cosine of the flight path angle, which we will call phi FPA. This geometry means that the flight path angle is measured slightly differently depending on which side of the orbit you are, but it's always defined in such a way to make this expression consistent, which also leads to these relationships for the cosine and the sine of the flight path angle. In the case of our small perturbation, we are assuming that the flight path angle is also a small quantity. We're going to use this setup in order to analyze the effects of this perturbation on the eccentricity vector of the orbit. Remember, we've previously shown that the eccentricity vector is equal to the orbital radius vector divided by the gravitational parameter of the central body times the quantity orbital velocity dotted with itself minus the gravitational parameter over the magnitude of the orbital radius plus the orbital radius dotted into the orbital velocity divided by the gravitational parameter, all in the direction of the velocity. We can express the components of the eccentricity vector in the Hill frame as, that is, the eccentricity vector component in the ER direction is given by RV squared over mu times cosine squared of the flight path angle minus 1. The E theta component of the eccentricity vector is given by RV squared over mu times sine of the flight path angle times cosine of the flight path angle. And the out of plane component of the eccentricity vector is 0 because the eccentricity vector lies entirely in the parafocal plane, which is the same plane as ER E theta. Without any perturbations, the magnitude of our eccentricity vector is strictly 0. We are on a circular orbit that has a 0 eccentricity. Similarly, the flight path angle is 0 everywhere. You can also see this in this diagram. The flight path angle at the turning points where the orbital radius and velocity are orthogonal is always 0. On a circular orbit, all points are turning points, and so the flight path angle is 0 everywhere. With perturbations to first order, we can write the components of our eccentricity vector in the Hill frame as, where we've just applied the first order expansion in all of the small quantities, delta v, delta r, and the flight path angle to the expressions that we previously wrote down for these components. So the eccentricity for small perturbations will now be non-zero, but will still be a very small quantity, assuming the perturbations are sufficiently small. Now recall our expression for the specific orbital energy. The specific energy is equal for all orbits to negative gravitational parameter over twice the semi-major axis, and is equal to the orbital velocity magnitude squared over 2 minus the gravitational parameter over the orbital radius vector. This allows us to solve for the semi-major axis as the reciprocal of 2 over r minus v squared over mu. This means that the natural log of A is equivalent to negative the natural log of this expression. And this allows us to write the associated differential term, dA over A, as negative of -2 over r1 squared times the variation in the orbital radius minus 2 times the circular orbit velocity over the gravitational parameter times the variation in the orbital velocity over 2 over r1 minus the circular orbit velocity squared over mu. Recall that the circular orbit velocity squared can be written as the gravitational parameter over the circular orbit radius, and therefore this denominator can be simplified to just the reciprocal of r1. This allows us to rewrite this differential expression as 2 delta r over r1 plus 2 times the circular orbit velocity times r1 over mu, all times delta v. As a final simplifying step, we notice that this r1 over mu term is the reciprocal of the circular orbit velocity squared, and so we can finally rewrite this expression as, so the variation of the semi-major axis scaled by the semi-major axis is equivalent to twice the variation in the orbital radius scaled by the original circular orbit radius plus twice the variation in the orbital velocity scaled by the original circular orbit velocity. As a final step, recall that the orbital period is given by 2 pi times the semi-major axis to the 3/2 power divided by the square root of the gravitational parameter, which means that the log of the orbital period is the log of the semi-major axis to the 3/2 power plus the log of 2 pi over root mu, where this whole term is a constant. And so the associated ratio of the variation in the orbital period scaled by the original orbital period of the circular reference orbit can be written as 3/2 the square root of a dA divided by a to the 3/2 power, which simplifies to, using our previous result for delta a over a, we can write. So to summarize, what we've shown here is that small deviations from the original circular orbit of the form delta radius, delta velocity will give us a small non-zero eccentricity and a modification to the eccentricity vector. They will give us a first order variation in the semi-major axis of the orbit. And similarly, they will give us a variation in the orbital period. And putting all this together, what you find is that for sufficiently small perturbations, you retain a closed orbit, but that orbit cannot remain circular, and so it must become an ellipse.